Hello everyone, my name is George, and today I'm going to be presenting on the Nobel Prize in Chemistry 2002 for mass spec. Odunola and I put together this presentation to go over the 2002 Nobel Prize in Chemistry. The prize was awarded to John Fenn, Koichi Tanaka, and Kurt Withridge for the chemical analysis of biomolecules. Dr. Withridge won the award for using nuclear magnetic resonance to elucidate the structure of proteins. But this presentation will focus on the work of Dr. Fenn and Dr. Tanaka. Dr. Fenn pioneered the use of electrospray ionization, or ESI, and Dr. Tanaka used soft laser desorption to ionize molecules for mass spec applications. We will start with the origins of mass spec. J.J. Thomson, who won a Nobel Prize in 1906 for his research on the discharge of electricity through gases, was also one of the first researchers to use mass spec to measure the mass of charged atoms. His work directly led to the discovery of the isotopic nature of atoms. Here on the bottom left is a diagram of the spectrometer Thomson used for these experiments. So here a voltage was applied to the gases that were kept in the cathode chamber. The ions were then accelerated through the spectrometer by an electric field. At the end of the machine was a fluorescent plate, which here on the right is what Thomson used to visualize the deflections of the gases. The deflection of the gases took the shape of parabolas, which moved in accordance to the x and y values derived from the equations shown here. The parallel field analyzer created a two-dimensional spectrum with a horizontal deflection x and a with a horizontal deflection x from the electric field of strength F, and the vertical deflection y from the magnetic field B. On the bottom right quadrant, you can see two individual parabolas for neon 22 and for neon 20. This was the first evidence of the isotopic nature of atoms. During World War II, mass spec was used to enrich uranium-235. Uranium tetrachloride was used because other uranium-containing compounds such as uranium oxide, were corrosive to the collutrons used. This is an example of a collutron, and each individual line here is one collutron used in this really big racetrack. So here uranium tetrachloride is ionized by rushing with high intensity electron beams, and it's sped up using a magnetic field normal to the ion source. The ion collectors were placed in relation to the arc made by the different momentum of the two uranium isotopes. Residual gas in this vacuum neutralized most of the ions so that positive charges didn't repel and spray the ions everywhere. Two different streams were formed from the uranium tetrachloride according to the difference in momentum caused by the two uranium isotopes. These collutrons produced 140 pounds of uranium-235 for the bomb dropped over Hiroshima. And interesting side bit, there were these uranium collutron girls who were a group of young women who worked at the Y-12 National Security Complex in Oak Ridge during the Manhattan Project in World War II. Their work involved operating collutron mass spectrometers, which were used to separate isotopes of uranium. So here, there's a picture of them that worked during World War II. So that was some history behind mass spec. So now we'll talk about one of the subjects of the 2002 Nobel Prize, electrospray ionization, or ESI. for short, operates by creating a fine aerosol of charged droplets from a liquid sample. This process begins with a sample being dissolved in a solvent and then pumped through a capillary tube. A high voltage is applied to the liquid as it emerges from the capillary tip, leading to the formation of a Taylor cone, where surface tension of the liquid is overcome by the electric field. As the solvent evaporates from the droplets, the charge on the surface becomes more concentrated, resulting in the formation of highly charged ions. These charged droplets eventually undergo a process called Coulombic fission, where the repulsive forces between the like charges causes the droplets to break apart into smaller and smaller droplets and eventually gas phase ions. These gas phase ions are then introduced into the mass spectrometer for analysis. So this ESI technique is favored for its gentle ionization process, which minimizes fragmentation, making it very suitable for studying the intact structure of large proteins. So here's a type of spectrum you can expect if you use ESI for your ionization method. On the left, you can see many peaks that correspond to different charges given to the molecule. ESI can assign charges ranging from +1 all the way up to +40. So John Fenn, which is the person who won the Nobel Prize, realized he could treat each peak as a measurement on its own and found a way to deconvolute the spectrum to give a precise mass measurement. So here on the left is a here on the left is a spectrum that hasn't been deconvoluted. As you can see, there's multiple peaks. The axes on each of these spectra is different. On the right is just mass. The labeled peaks correspond to calmodulin bound to the increasing number of calcium 2+ ions. As you can see, if this was a regular mass to charge spectra, these would be very far apart. But once you're able to deconvolute the spectrum, you can see very much clearly that each one of the peaks correspond to a different protein with a different number of calcium ions bound to it. So the other side of the Nobel Prize, in soft laser desorption, a sample is placed on a target surface and is typically mixed with a matrix compound that absorbs the laser energy and helps deabsorb and ionize the sample molecules. The energy is absorbed by the matrix, causing it to vaporize, and also some of the energy that's absorbed into the matrix is transferred over to the sample molecules, and then therefore ionizing it. So this can then carry the sample molecules with it into the gas phase. So as the samples are ionized by processes such as protonation, deprotonation, or any type of interaction with the matrix, this results in the formation of gas phase ions, which then can be analyzed by a mass spec to determine the mass to charge ratio of the molecules. In soft laser desorption, or specifically MALDI, as you will see, here you can have the time of flight, or the time it takes for the ionized molecules to reach the detector. This can be translated into mass to charge ratios, which I will explain further in the next few slides.
The MALDI-TOF process is a two-phase procedure. Initially, the samples are fixed in a crystalline matrix. In the initial ionization step, they're bombarded by a laser. The sample molecules vaporize into the vacuum while being ionized at the same time. High voltage is then applied to accelerate the charged particles. The second step is the time-of-flight mass spectrometry phase. In the linear mode, particles will impinge upon the linear detector within a few nanoseconds after ionization. Higher mass molecules will arrive later than lighter ones. Flight time measurements make it possible to determine molecular masses directly. Each peak in the spectrum corresponds to the specific mass of the particle along the time axis, starting with the ionization moment. In the reflector mode, the particles are diverted so that they fly towards a second detector. In addition to extending the flight distance, the reflector also focuses the masses. The combination of these two effects makes for higher resolution than in the linear node.
So here, a conventional tissue section is coated with a matrix, which extracts molecules from the tissue using MALDI-TOF. So afterwards, the sample is measured in a raster process in the mass spec, resulting in the spatially resolved mass spectrum. And so the UV laser only hits the matrix crystals, so it actually leaves the actual tissue on its own. So subsequent to the MALDI measurement, histological staining is carried out, therefore allowing a histology-directed analysis of the mass spec. These color signals allow the detection of patterns, which represent the distribution in tissue of the molecule of interest. So this visualization is very close to what can be seen in immunohistochemistry, but in contrast with the advantage that multiple molecules can be examined by one measurement. So here, this peak is found in almost all of the tissue. This one is found in the upper quadrant, and then this one's found at the bottom, and so and so and so. So this can help doctors see what type of proteins or really anything is present in particular sections of a tissue. So here I will highlight the importance of choosing the correct matrix for your compound of interest, as it influences the quality of your resulting mass spectrum. So here on the left you have cinepinic acid, and on the right you have dihydrobenzoic acid. You can see dihydrobenzoic acid wasn't a right fit for Streptomyces cerevisiae, and cinepinic acid was. So a suitable matrix should be able to absorb the laser wavelength employed by MALDI, and it should also be able to gently ionize your analytes to prevent fragmentation. And it should also be able to yield a high signal-to-noise ratio where you want it. So here, maybe the case would be that dihydrobenzoic acid could give a really nice spectra in the higher mass to charge ratios, but in this case, for Streptomyces cerevisiae, it's more important here in this range where cinepinic acid is a much better matrix. And it's also important that the matrix should also crystallize uniformly on the sample to be able to reproduce ionization and also spectra. So MALDI is being applied in several fields. Here in this slide, the clinical procedure, or at least the standard clinical procedure, was to isolate protein extracts from sample bacteria and then run the protein extracts on the SCH page shell to then be able to separate them using mass spec and also ionizing through a pulsed laser. So this process of making them SCH page extract can be very, very much tedious. So what they've done here is now, through being able to spot the protein extract directly onto the matrix and then using MALDI-TOF, you can have this process done in one step instead of having to run an STS page. So the same spectra can be obtained in less steps. Multitop has also been used in it's also been used in pharmaceutical analysis, so being able to discover new drugs, and it's also been used in environmental analysis, as it's very useful for detecting pollutant, pesticides, and other environmental contaminants. It's also very rapid and sensitive, so it's very important for these kind of analysis. It's also been used in food science, material science, and interestingly enough, it's also been used in forensic science, where it's been used to trace evidence such as fibers, drugs, and explosives. So this is a very interesting and powerful tool. MALDI-TOF isn't in a vacuum, so there's other techniques that are used to improve the spectrum gained from using MALDI-TOF. For example, FTIR spectroscopy has been used. So this is Fourier transformation IR spectroscopy. It measures the absorption of infrared radiation by the sample material, which can be used to identify functional groups and also a bunch of different molecular bonds present in the sample. When used in combination with MALDI, it can provide complementary information about the chemical composition of the structure of the sample. And this has been used to be able to differentiate between very closely related species, as you can see here on the right. Even though species might be very similar, this combination is able to provide enough data to be able to differentiate between two very closely related species. Thank you guys for watching.